Okay, guys, welcome. Today we're going to talk about logarithmic functions, right? Now, the way that we're going to talk about logarithms are the fact that they're the inverse functions of exponential functions. So if you haven't seen the video on inverse functions, you might want to review that. Or if you want a refresher, you can check that out also, right? Now, the idea behind a logarithm is that we have that. I'm just going to write this up here just so it's a little bit more clear. We have that y is equal to log base a of x if and only if, or I'm going to say that it's equivalent. I'm going to use this sort of double arrow over and over again. It's equivalent to saying that x is equal to a to the y. Now, if you can master this definition, this is 95% of the battle when it comes to logarithms, right? And sort of an easy way to think of this is that if you have, let's put it this way. So I'm going to rewrite it down here, and I'm going to color code here. So if I have y is equal to log with base a, and that is of x, that looks too similar. Let's use this color. Then that's equivalent to this definition. And then I should put my equals here, x here before I change that color back to the y. Whoops. Okay, let's try this again, and then that y should be purple. Okay, there we go. Now, sort of the easy way to remember this transition is that just remember that logarithms and exponentials are inverses of each other. So this x is with the log, right? The x is with the logarithm, but it's not with the exponent. Right? And then the y is not with the log, but it is with the exponent. And your base a is the base in both cases, right? The only thing that's switching places is the x and the y, which is what you do when you take the inverse, right? So you have that your x is with your logarithm in this case, so therefore it's not with your exponential, right? It's on the other side of the equal sign, right? And then your y is on the other side of the equal sign with the log, but it's on the same side with the exponent, right? Some other things that we should mention here are that if you have a logarithm where there's no base, so if it just says something like log x, that means that you have log base 10, right? So if there's no base written, it's log base 10, and we call this a common logarithm. And if you have the notation ln of x, that's a log with base e, that number that we talked about in the previous video, and this is a natural logarithm. Right? So just be aware of those two things because they will come up. Okay, so let's do a couple of examples where we're going to write some of these logarithms in exponential form. All right, so first let's start off with log base 3 of 9 is equal to 2. All right, and I basically want to fill in the other statement. Well, my base is still my base, so my base is still going to be 3. Now my 2 is not with my log, so that has to be with my exponent. And then my 9 is with my log, so that better not be with my exponent. Right, and of course we know that this makes sense because 3 squared is 9, right? Sort of going in this direction is nice because we end up with something familiar, right? Let's look at part B. We have log base 2 of 1 over 8 is equal to negative 3. Right, well, same process. 2 is still my base. My negative 3 is not with my log, so I'm going to make it with my exponent. And my 1 over 8 is with my log, so I'm going to make it not with my exponent. And of course, 2 to the negative 3 is 1 over 8, so we know that that's correct. Right? Then we have log base 16 of 4 is equal to 1/2. So if we convert this, we're going to get 16 to the 1/2 is equal to 4, right? My exponent is now 1/2 since that wasn't with my log, and my 4 is now on the other side of the equal sign because that was with my log. Right, now in part D, we have ln of 7.39 is equal to 2. Right, well first just remember that log base e is the same thing as ln. So if we convert this, this is saying that we have e squared is equal to 7.39. All right, and then finally part E, we have that log base 10 of 5 is 0.7. So this means that if I take 10 and I raise it to the 0.7, I'm going to get 5. All right, so that's what we mean by that. Okay, now let's go in the other direction. So now we're going to be given an exponential equation. We want to write it in logarithmic form. All right, so in part A, we have 36 is equal to 6 squared. So when I transform this, my base is still my base, so this is a log base 6. Now, since the squared is with my 6, my exponent of 2, I need the 2 to not be with my log here. And since 36 is not with my exponential, I want it to be with my log. So I have log base 6 of 36 is equal to 2. Right, and of course this is usually a little bit more tricky to think of because we're not as familiar with logarithms as we are with exponents. Okay, now in part B, we have 7 is equal to the square root of 49. Now here we have to be a little bit clever and think of how can we write a square root as a power? Well, of course, we can write that as 1/2. So that means we have a log, my base is still my base, so log base 49. My 7 is not with my exponent, so it's with my log. And my 1/2 is with my exponent, so it's not with my log. So log base 49 of 7 is 1/2. Okay, part C, we have 1 over 16 is equal to 4 to the negative 2. So of course, this will be a log base 4 of 1 over 16 is equal to negative 2. And then part D, we have a 0.1353 is equal to e to the negative 2. So this would become a log base e of 0.1353 is equal to negative 2. Right, and of course, if you wanted to, since this is a log base e, we could say even that this is natural log of 0.1353 is equal to negative 2. Either one of these would be good. All right, so that's converting from exponential to logarithmic form. And this is a huge key in understanding logarithms. Okay, now let's solve some simple logarithmic equations for x. So we have log base 3 of x is equal to negative 2. Well, how do you think we're going to solve this? We're going to convert it to exponential form. So if we convert it, my base is still my base. The thing that's not with the log is now with the exponent, and the thing that's with the log is now not with the exponent. So then we get 3 to the negative 2, which is 1 over 3 squared is equal to x. So then we get that 1 over 9 is our x value here. All right, let's take a look at part B. Part B, we have 5, sorry, let me write this out. Log base 5 of 125 is equal to x. So now if we convert, we're going to get that 5 to the x is equal to 125. Right? Well, of course, 125 is a perfect power of 5, and we get that x is equal to 3. Okay, part C, we have log base x of 81 is equal to 4. So if we convert this, we get that x to the fourth is equal to 81. So here, if we take a fourth root, you'll eventually find that x is equal to a positive 3, right? And we're just taking the principal root here, right? And then, of course, you want the principal root here. I should be specific. You want the principal root because if you have a negative for your base, that's not defined, right? Okay, and then part D, we have ln of x is equal to 1/2. So if we convert this, remember that ln is a base of e. So this is e to the 1/2 is equal to x. So for this, we need the calculator, right? So I need to do e to the 1/2. And again, if you're going to do 1 divided by 2, you want to think of it all being in the same set of parentheses. But if we do this, we get x is about 1.6487. And I should use approximately. All right, so those are some simple log equations. Okay, now some log identities that we're going to need look something like this, right? So the first one says that if I have a to the log base a of x, the a and the log base a essentially cancel and I'm left with x, right? Now to see this, just convert it to logarithmic form. If you convert this, you're going to get this is log base a of x is equal to log base a of x, which obviously is true, right? So of course, since this is true, right? So that's a nice sort of jump that we can make there. All right, and that will be useful. Next one is that if we have log base a of a to the x, that's equal to x, right? So of course, to see this, let's convert it, and this will be a to the x is equal to a to the x, right? So of course, since that's true, so is this. All right, so the third one, I shouldn't say part C, this is log base a of a is equal to 1. And if you convert this, this says that a to the first is equal to a, which of course is true. And then for the last one, we have a log base a of 1 is equal to 0. And if we convert this, we get a to the 0 is equal to 1, which of course is true, right? So these are all statements that we can show to be true by using their opposite form, whether that's exponential or logarithmic form. So to see a couple of these in practice, part A, we have 8 to the log base 8 of 5. Now, of course, you could show that this is equal to 5 using exponential form, but we know that this 8 and this log base 8 essentially cancel, and I'm left with 5. Okay, in part B, we have a log of 10 to the negative third. Now, since there's no log, since there's no base indicated there, we know that it's base 10. Now, the log base 10 and the 10 to a power, they essentially cancel, and we're left with negative 3. And of course, if you wanted to, you could also show that by converting, but I'm just sort of using the properties here. Now, part C, we have log base 7 of 7. And of course, log base 7 of 7 is just 1. Right? And again, you could show this by converting to exponential form. And if you convert it to exponential form now, you would even have 7 to the 1 is equal to 7, which is true. And then finally, part D, we have log base 4 of 1. And of course, this is always 0. All right, so those are some simple log identities that we can use. Okay, so let's go ahead and let's sketch a graph of what a logarithm looks like. So we're going to sketch log base 2 of x. Now, of course, we can think of this as y equals log base 2 of x. But what does it mean if we have log base 2 of x? Well, you guessed it, we're going to convert it, and this is 2 to the y is equal to x. So now we have an equation where x is by itself So when I make my table of values, I'm going to test easy values of y. So now my x values, for example, will be 2 to the negative 2, which is 1 over 2 squared, which is 1 over 4. When I plug in negative 1, I'm going to get 1 over 2 to the 1, which is just 1 over 2. Then I'm going to get 2 to the 0, which is 1, 2 to the 1, which is 2, and 2 squared, which is 4. All right, so let's go ahead and we'll graph this. All right, now all my x values are positive. Right? 1/4, 1/2, 1, 1, 2, and 4, they're all positive. So let's go ahead and plot these points. So the first one I have is 1/4 negative 2. So that's going to look something like this. Then I have 1/2 negative 1. So that's going to be here. And then I have 1 comma 0. So that's here. I have 2 comma 1, which is here. And I have 4 comma 2, which is like here. So we get something like this. Right? And of course, this looks familiar. This looks like an exponential function just tilted on its side. And that's, of course, exactly what it is. If you were to reflect over this line, this y equals x line, you would get this. Right? And you get sort of the mirror image over that y equals x. And this would be the graph of y equals 2 to the x, right? Because they're inverses of each other. So that's how we can sort of use the inverse and the definition of logarithms to graph a logarithmic equation. Okay, now a lot of these properties of logarithmic functions we can really get from the properties of exponential functions and using the fact that they're inverses, right? So on a logarithmic function, you always have the point 1 comma 0, right? And that's because log of any base of 1 is always equal to 0, right? And again, remember that on the exponential, 0 comma 1 was always a point, right? So that makes sense. Now for logarithms, you have that the domain is all positive numbers and the range is everything, right? And of course, for exponentials, it was the opposite, right? You could only have positive numbers come out, but you could put any number in. For a logarithm, you can only put positive numbers in, but any number can come out, right? Now your base properties still work the same way. If your base a is bigger than 1, then you have an increasing function. If your a is between 0 and 1, then it's a decreasing function, right? And then finally, we get the nice properties that we had before, where if we have something like log base a of x equals log base a of y, then we're saying that log of something is equal to log of something. And that really means that those somethings have to be equal, right? And then, of course, we also get the property that if we have log base a of something equals log base b of the same something, then that really means that a and b have to be the same, right? So you can't get sort of like this more than one property happening. And again, that becomes evident in the fact that both of these are one-to-one functions. So for example, in part A, we have log base 5 of x plus 1 is equal to log base 5 of 25. Well, since both of the bases are equal, this means that x plus 1 and 25 have to be equal. So once we subtract 1, we get that x is equal to, wait a second here. So x plus 1 is equal to 25, right? So then x has to equal 24 once we subtract. Right? And then part B, we have log base x minus 1 of 31 is equal to log base 5 of 31. So since both of these logs are of 31, that means that the bases have to be equal. We get x minus 1 is equal to 5. So if we add 1, we get x is equal to 6. All right, so those are using some of those log properties there. So that concludes this video on logarithmic functions. I hope you enjoyed, and I will see you next time.